Hi everyone, just looking today at a more sophisticated way to deal with angles. So here's your warm-up question. What I'd like you to do is to pause the video, have a go at this question, and when you're ready, have a look at the solution. Alright, so you've had a go at this question. You've used what you already know from earlier years about finding part of the circumference of a circle to come up with theta equals 47.75 degrees. Now we're going to come back to this example later on. Write down anything you need and then come back to the video again. Okay, so what we're using so far heaps in our trigonometry is these things here. We've got our exact ratio triangles and we've got our sine and cos curves. We've got tan as well, but just let's focus on sine and cos today. I've forgotten my 60-degree angle in here. But using these things, I can easily ask you a question. I can say, what is sine of 30? And you will say sine of 30 degrees equals the opposite over the hypotenuse equals a half. Or I could say to you, what's cos of 90? And you'll look at the picture and you go, well, cos of 90 is 0. So cos of 90 degrees equals 0. So we're pretty familiar with that kind of thing. That's what we've been doing. But what we really need is a more sophisticated way to talk about these angles, because if you look carefully, we've got different units on our x and y axis. So on our y axis we've got this number 1 and minus 1, so we've got these units, and then we've got degrees on the x axis. What will be really handy is if we can get something better than degrees on this x axis, some other kind of unit, maybe one that works better with the number 1. And this is where this word radian comes in, and we've seen this on our calculators for years and not really known what it was. So let's have a look at what we mean by a radian. So the definition of a radian is that it's the measure of the ratio of the arc length to the radius. And we could write that as that angle at the centre is equal to L, the length of the arc, over r, the radius. Now keep in mind that r is the letter we use for radius, so we can't start using r for radian. We're going to need another word for that, and we'll come back to that. You will get something nice for that later. So for our warm-up question, what we could have said was that angle AOB is equal to 2.5, which was the length of the arc, over 3. And when we do 2.5 divided by 3, our calculator gives us 0.83 repeater radians. This could have been written as 0.83 rad or a little c. So I could have written that as theta equals 0.83 repeater. And that just is meant to be part of a circle, which is exactly what it stands for. So if we now think about an entire circle, we could say that angle AOB, the angle at the centre, and let's put a circle here, here's our circle. The angle at the centre is 360 degrees. It's equal to the circumference over the radius. That's our definition of radian. So our 360 degrees on the left would be equal to 2 pi r over r. Let me write that a bit more clearly. 2 pi r, we know that's the circumference of a circle over the radius. These things cancel out, and what we're left with is that 360 degrees equals 2 pi radians. We can divide both sides by 2 and find that 180 degrees equals pi radians. This is our magic rule now for radians, is that pi radians equals 180 degrees, and that's all we really need to remember about radians. Everything else can follow on from there. What things can follow on? Well, I could have written it like that. I can now think about some other angles. I could say that pi on 2 radians is 90 degrees, pi on 4 is 45, and so on. And there's some examples there that you might like to copy down. But even more powerful than that, and really useful to us, is that we can now go back to what we already know about trigonometry, and we can now write our y equals sine x curve, but instead of having 360 degrees, we'll have 2 pi. We'll have pi. Here we can have pi. We can have 2 pi. We could have pi on 2, 3 pi on 2, and so on. In this triangle, instead of 30 degrees, we can have pi on 6, pi on 3. Instead of 60 degrees, same numbers here, 1, 1, square root 2, square root, what have we got here, pi on 4, and so on. Now just lastly, you can test this on your calculators, put it in radian mode, and when you do sine of pi on 4, you should get 1 on square root 2, and when you're in degree mode, sine of 45, 1 on square root 2. Can you go on now please with the exercises that we've set from 4A. Hope it all goes well. Bye.